In this video, we're going to take a look at CPU performance. So first things first, we've got two types of instruction sets that a CPU can have. So a RISC processor is a reduced instruction set computer. A CISC is a complex instruction set computer. RISC, obviously being reduced, has fewer instructions. A complex one has more. Now, as far as I'm aware, and I could be wrong with this, but I'm pretty sure that most modern CPUs are RISC because of the simple architecture used to make it. But RISC is preferred because you write less instructions, because one piece of code, usually in assembly language at least, is one instruction. Whereas CISC might take multiple for one line of code, so have multiple instructions. So if there's less instructions, there's fewer cycles, less cooling, less power, faster you could say. It's simpler to make and it pulls a lot less power, which is good for money, energy usage, lots of different things really. On top of that, we have a thing called clock speed. So in the previous video, we looked at how the clock synchronizes all those components, all those registers, buses, and how they work. Each time the clock does a clock pulse, that is an enable signal, which tells the computer to do something. Okay, that keeps everything in sync, and you look at that in a little bit more detail further on in the course. Now, the speed of the clock is measured in megahertz or gigahertz, and typically the faster the better. The more instructions you get done in a short amount of time, the more things you can do, in theory, but that's not always the case. If you do have a high clock speed, if you overclock your computer, you have to use more power, so you might need a better power supply. You might need more cooling, and you're going to spend a lot more electricity. So if you're paying the bill, overclocking might not be the best idea. Because it's working a lot harder, if you was constantly sprinting, you'd get hotter and you'd get tired. Same with your computer. So if you overclock your CPU, it might not last as long. You might not get that longevity. The other part of the CPU is a thing called cache memory. This is a small section of memory that's really, really quick, and it's located in the CPU or very close to the CPU, but it'll be inside your little square that you put into your computer. Now, it's where, if you're using lots of data, it goes in the cache. As I said in the example, if I'm marking a bunch of books, I'm going to put them close to me because I'm still using them. Now, because it's like RAM but not RAM, it is faster because it uses a different type of RAM, which we'll look at later on. Level 1 cache is the fastest, costs the most. You've got level 2, level 3. So if you go look up, I recommend you pause the video, look at some CPUs, have a look at how much level 1, 2, or 3, or just cache you've got. Usually, the more cache you've got, the better the CPU and the more expensive it is. If I wasn't keeping my books nearby, I would have to go to the filing cabinet or the room they're located and get them one at a time. That'd slow me down. Same as RAM. Now, level 1 cache, we split that into instruction cache and data cache, so we can fetch things at the same time. The more cache memory there is, the more likely, the higher chance that it doesn't have to go fetch something from RAM, that it's already got it in that super fast memory already, so it can get it a lot faster, which is always good. You then got your CPU cores. Not technically true, but if you think of a CPU as a brain, you can do one thought at a time. You can't do multiple things. If you've got two processors, or two CPUs, or more cores, sorry, then you can do two things at once. 8 cores, 16 cores, whatever you've got is the more things you can do. However, let's say that if one brain is waiting for the second brain to finish something before it can carry on, then you may as well just have one core doing it. So if you've got one really fast processor, but you've got 4 not so fast processors or not so fast cores, then is it going to be any faster? So there is a trade-off there. Now, if we have multiple cores, we can do a thing called parallel processing. This is where we use lots of our cores, as many cores as we can, at the same time or in quick succession. This means that one part of the CPU can focus on something, whilst the other part of the processor can focus on something else, and they can work together. However, sometimes instructions can't be done at the same time. Therefore, it's not always possible, so it's not always quick. But most of the time, I'd say on average it is. Now, how we store things in the computer are things called words. Now, a word in CPU terms is just a small number of bytes that can be handled by the computer. Now, how long that word is, or how much memory can be stored, depends on the computer you've got. So, 32-bit architecture, 64, x86, basically is the word length in simple terms. Now, you're not necessarily going to get asked what a word is, but it's a useful term to know. Another contributing factor to speed is bus width. So that's how much data can you send at a time. Think of the width of a road. If you've got 3 lanes, that's 3 buses or 3 sets of people being transferred. So when we're looking at the address bus, it's the number of bits used to define how many addresses we can use, and the bus width is the same as the word length, but sometimes it might be half. And the width of the address bus determines how many places we can go to, how many possible memory addresses there are. With an 8-bit address, we can have 256 memory addresses. The data bus is bidirectional. We can send things to and from RAM, or to off and from a location, and essentially is how many wires there is that we can send things down. If the data bus is the same width as a computer word, we can send data and retrieve data in one go. That's pretty much it. We're just over the 6-minute mark, so not really 5 minutes. Could say it's a bit of a lie in the description, but please like and subscribe, and I'll see you in the next video.